we're going to take a look at derivatives and the graphs of derivatives, which we kind of did already. We talked yesterday about derivatives of a function being another function. So we can find the slope of the tangent line at each point of a curve and plot all of those slopes, and we get this new function that we call the derivative. And the graph of the derivative is going to be very closely related to the graph of the original function. And so we want to be able to recognize some of the features of those graphs. So if we have something like this is just a parabola. This is y equals x squared. And we took the derivative of this yesterday. So we actually figured out what the derivative was. But just looking at the graph, let's kind of get an idea of what the derivative of this function might look like. Where are some points, or where is a point that it would be easy to take the derivative just by looking at the graph? Ben?
The origin.
Yeah, at the origin. What's going on at the origin there?
The parabola has a slope of 0.
Okay, so the slope of the parabola here is 0. I can draw in a tangent line here if you want to see it. Anytime we have a maximum or minimum on a curve, on a smooth curve, we're going to have a derivative that is 0. So I'm going to plot some points for the derivative using red here. Besides that, just looking at the graph, it's kind of hard to tell exactly what the slope is, but we can kind of see a pattern here. We can see what's going on. If I look at the slope just a little bit to the right of 0, what's the slope going to be? First of all, positive or negative?
Positive.
Is it going to be a big positive or a little positive? It's going to be a little positive, right? So just a little bit to the right of 0, we might have a tangent line that looks like this. So it's going to have a small positive slope. As I move away from the origin, though, what's going to happen to the slope? Like there, and then here, and further. What's happening to the slope? It's getting steeper, right? It's increasing. All right, so as we move away, we're going to be getting slopes that are getting bigger and bigger and bigger, right? You guys agree with that? Now, I'm drawing them as a line, partly because I know it's going to be a line, personally. And you guys, if you remember from yesterday, we got a line for this. We don't necessarily know, looking at the graph, that this is going to be a linear relationship, but we do know that it's increasing. We do know that as we move further to the right on the parabola, the slope is going to get bigger and bigger. And as we move to the left, just a little bit to the left of the origin, we're going to have a slope that is negative, but just a little bit, right? And as we move further and further to the left, they're going to be negative, but steeper and steeper, so bigger and bigger negative numbers. So we're going to have the same type of relationship going to the left, looking like this. Okay, does that make sense? So what do we expect the picture of our derivative to look like? Regardless of whether it's a line or not, what's going to be happening with this derivative? What word can we describe this derivative? It starts with an I.
Increasing.
It's increasing. So the derivative is increasing because as we move from left to right on the original curve, the slope is always getting bigger. It's becoming a smaller negative number, which means that it's increasing to the left of the origin, and to the right, it's becoming a bigger positive number. So we know that the derivative is going to be increasing. We also knew that the derivative was going to be negative here, because the slope of the tangent lines are going to be negative. We knew that the derivative was going to be positive here, and we knew the slope of the derivative was going to be 0 here. So some things that we want to look at when we're considering, bless you, what the derivative is going to look like is whether the slopes are increasing or decreasing, whether the slopes are positive or negative or 0. And we should be able to recognize those things at least. So we get a derivative that ends up looking like this. Okay, let's look at another one. This one's a little bit more complicated, right? If I were to ask you to sketch the derivative of something like this, what would be a good thing to start with? What do you think, Carly? Yeah, I would start with the maximums and minimums. So if we go to every point where we're going to have a maximum or a minimum, we know that the derivative at those points is going to be what? 0. So at those points, we're going to have a point on the derivative that is going to be 0. So the derivative is going to have zeros at these points, roughly. Okay, now, between those points, they're not going to be zero. They're either going to be positive or negative, or it's going to be positive or negative. So let's just look to the left here. To the left of this point, is the derivative going to be positive or negative? It's going to be positive because the slope of this curve right here is positive, right? Remember, when I say slope of the curve, what I really mean is slope of the tangent line to the curve. All right, so the slope's going to be positive, and we can also see that the slope is decreasing because it's a really big positive number here. It's a slightly less positive number here, less positive here, all the way to zero. So to the left of that point, we should get a derivative that looks something like that. You guys agree with that? No, this is a very rough sketch, but it should look something like that. Now, you could probably guess the derivative is going to end up being a smooth curve. We have a smooth curve here. Usually when we have a smooth curve, the derivative is going to be smooth also. So would you expect the derivative to bounce here? I mean, just knowing that, it's not. But we can look at the slope here. The slopes between here are going to be what? Negative. So we would expect the derivative to go below the x-axis, something like that. And then we can see that between this point and this point, the derivative is going to be positive, so it's going to go above the x-axis. And then between here and here, it's going to be negative, so it's going to be below the x-axis. We can also see here that it becomes more negative here. The slope is steeper here than it was over here. So we would expect the derivative to go down lower to attain lower values. So we might see something like that. And then to the right of this, what do you expect? Yeah, it's going to be positive. And actually, the slope gets pretty steep pretty quick. So it's going to go up and increase something like that. So we would expect our derivative to look something like that. Here's what it actually looks like. Is it pretty close? I can go back for you here. I think. There we go. I think we got pretty much all the right features, right? Okay. How about something like this? This is my favorite one. So, first of all, the slope here is always going to be what? It's always positive. Now, over here, it's just barely positive, right? It's almost a horizontal line here. So what's the slope going to be over here? It's going to be positive, but really close to zero, okay? So in this region, we're going to have slopes that are really close to zero. Right here, I want to make sure I get a straight line on this. Right here, missed it. The slope looks like it's about what? Okay, so the slope looks like it's about 1 there. So I'm going to put a graph or a point for the derivative there. Over here, what's happening to the slope? It's getting bigger, right? So right about here, it looks to me like the slope is about 3 maybe, because it's going, that point's going through the origin and then tangent right about there, so the slope's about 3. So we would get a point on the derivative right about there. What do you notice is happening? It's the same. Anybody know what this function is? Not log. It's the exponential function. It's e to the x. So it actually turns out that the derivative of e to the x is e to the x. So it's its own derivative. So the slope of the tangent line at any one of these points is actually the value of that, the value of the function at that point. We'll get to that later about why that happens, but that's the only function that's true. It's the only function that it's its own derivative, besides 0. Because the line y equals 0 is a horizontal line, and the slope of a horizontal line is 0. So that's actually its own derivative also. Okay, so this is the derivative of itself. Kind of fun. Okay, how about this one? Is this going to be the same thing? This is the log function, by the way. Natural log. Do you think this is going to be the same? No. It's definitely not going to be the same. We can tell right away it's not the same because the slope of the tangent line, say right here, is what? I don't need specifics, but it's positive, right? Okay, so we're going to have a positive. Now, over here, it's a really big positive, right? This is almost a vertical line, and the slope of a vertical line is undefined, or in calculus terms, we might say it's infinite, right? So the slope of a vertical line is infinite, and so what we're going to end up with is a function that starts up here. The derivative is going to be up there. Now, what's going to happen like around here? What's the slope here? What does it look like? It's 1. It actually, the slope here corresponds to the slope of the 0.01 on the e to the x curve. So it's going to be really big positive here, and it's going to come down through 1. Oh, that's not 1. Sorry. Is the slope ever going to become negative? No. So the slope's decreasing, right? It's flattening out more and more, but the slope is never going to become negative. So what's going to happen here with this? It's going to approach 0. So what we end up with is a vertical asymptote here on the y-axis and a horizontal asymptote on the x-axis. Now, this original function, that was the log function. What does this look like? Anybody know? It's a function that you ought to know. That's 1 over x. It's the right branch of 1 over x. Now, the other side would be over here, but that part doesn't exist here because the log function is not defined for negative numbers. But it actually turns out that the derivative of the log function is 1 over x. Kind of another cool connection there. So it should look something like that. How about something like this? This is the tangent function, more or less, with some stretches in there. What's the derivative always going to be for the tangent function? It's always positive, yeah. So you can see that this function is always increasing, right? So it doesn't matter where we are in the branch, it's always increasing. Where is it increasing the most? Where's the derivative going to be the biggest? Yeah, on the outsides, right? Near the asymptotes. We're going to have the most vertical tangent, so that's where the derivative is going to be the biggest. So if I were to draw in some asymptotes here, that's probably not where the asymptote is, but it's close. That's better. So if I were going to draw that in, the slope is the biggest over here, close to the asymptote to the left, and then also over here. Where is it the smallest? The origin, or what would be another way of describing that? Because it's not just at the origin. Yeah, halfway between the asymptotes, right? So in this case, that's going to be the origin. But halfway between the asymptote, that's where it's the flattest, so it's going to be the lowest. So it's going to be really big here, it's going to be really big here, but in between it's going to come down. And what we're going to end up with is a kind of a U pattern that repeats over and over again. Okay, we'll get into that later. That's close to the secant function. It actually turns out that it's secant squared. It's not just secant, but it turns into secant squared. So you can see here that this derivative indicates that we have a really steep slope, but it's positive near the asymptote to the left, and the slope decreases to its least value, still positive though, halfway between the asymptotes, and then really high at the ends. Okay. The main point of that is I wanted you to see just a visual of the connection between a function and its derivative. You should be able to look at a function and at least get the major features of the derivative. You're not going to get it exact just looking at a graph because it's really impossible for you to measure the slope of the graph at any point. You could make some guesses, you could draw in some tangent lines and try to be more accurate, but I'm not going to be worried about accuracy. However, I will ask you to do two things. I'll ask you to take a function and just make a rough sketch of what the derivative should look like. And when I'm looking at that, I'll be looking mostly at zeros and positive and negative slopes. So whether it's on the x-axis or above the x-axis or below the x-axis. And then I'll also ask you to match a function to its derivative. So if I'll give you a few pictures, I'll give you a picture of a function, give you a few pictures of what the derivative might be, you pick which one is the actual derivative. That's something that I will ask you to do.